So I have the honor and privilege to introduce the keynote speaker today. And Billy's been here before at the Design and Medical Device Conference Innovation Week. And you know, it's always fun to listen to him give his presentations. And you know, it's been in the news lately, the total artificial heart. So I asked if he could come and tell us kind of the story from, you know, innovation to preclinical to now the clinical trials. He's a cardiac surgeon. He's, you know, runs the Texas Innovation Center there. He's worked with J&J. I mean, he's got 200 plus patents. But I think the key thing about Billy is his energy, his enthusiasm, and how he inspires people. And, you know, I've been down in Texas, and he inspires the next generation of innovators. And so I think it's that key thing that he does where you want someone like him to be your keynote for a conference like this. So with that, Billy, I'm looking forward to your presentation.
Best introduction ever. Thank you, Paul. I'm really honored to be here. I have been to this meeting several times in the past. I always love it. Paul does a great job. There's so much energy and cool stuff going on here. And I really like it this time because my 91-year-old mother is here. She actually slapped my hand when I tried to have a second dessert. So, you know, it's still that sort of relationship. I love talking about this topic. This is my Grail quest. This is something I've been working on for over 20 years. Another thing, I always give talks, and my mom says, you had too many slides and you talk too fast. I've got way too many slides, and I'm going to talk really fast. My lovely wife got me a T-shirt that says, help, I'm talking, and I can't shut up. But this is my favorite topic to talk about, and so I hope you'll indulge me. This is the past, the present, and the future of the artificial heart. This is something we've been working on for a long time, and I think we've got a glimpse of what the future of this field will be, and I think we have in our hands now the first practical, permanent heart replacement device, not to keep you alive until you get a transplant, but instead of a transplant. And I'm going to tell you where we've been, what we've done just in the last year, and where I think we're headed. Here's my disclosure. I'm severely conflicted. I'll try to maintain equipoise. I think everybody here knows that heart failure is a big deal. Everybody in this room has somebody that's been touched by heart failure, and about a third of you are going to die of heart failure, and I'll tell you which ones. So why don't we just transplant them all? Because there aren't enough hearts. And this is an old slide. The number of transplants we've been doing in the United States has continued to increase. It's close to 5,000 a year now. Why? Opioid crisis, more donors. We're now using donation after cardiac death, hearts of people that have already died. We wait 5 minutes and take them out and reanimate them, and the results are quite good. We have these organ transport containers. We now know that we can use hepatitis C donor organs, a lot of factors. But 5,000 for 130,000 people that die every year in the United States of heart failure. So it hasn't had an epidemiological impact. So why don't we just make an artificial heart? That's not a new idea. People have been trying for decades. My old boss, Michael DeBakey, have you all heard the name Michael DeBakey? Just a sweetheart of a guy, heart surgeon who was just indefatigable, super hardworking. I was his last chief resident. He was working with a Argentinian surgeon, Domingo Leota, on this device. And he had hired Denton Cooley, another very famous heart surgeon, who was my partner for the last 8 years of Dr. Cooley's life. And Dr. Cooley came down, and I think he didn't like working for an academic medical center because you had to give half your money to the medical school. So Domingo Leota was frustrated because Dr. DeBakey was very methodical and very academic in his approach, and it was taking him a long time to get through animal work. So while Michael DeBakey was in Washington, D.C. getting additional funding from LBJ, Denton Cooley famously sewed it into a patient without permission. Dr. DeBakey came back and was very congratulatory. No, not really. He fired Denton Cooley. He fired everybody in the lab. They all jumped over to the Texas Heart Institute, which was the lifeboat. They were separated by a parking lot. And for the next 40 years, the two of them didn't speak. And because of that competition, the two of them did more heart surgery together throughout the 80s than was done in all of Europe. They were the two busiest heart surgeons in the world and had this iron curtain between their facilities that you could throw a frisbee from one to the other. This was a gravely ill gentleman, a very brave man, Haskell Karp. He was 46. He'd had a massive heart attack. There was an operation where you cut off the dead heart that was stretching out and replace it with Dacron. And you could get some patients through, but the amount of heart that Haskell Karp had involved with this was too great. Didn't Cooley realize he probably wasn't going to survive? And he talked to the Karp family and said, listen, if you won't come off the heart-lung machine at the end of this operation, I would like to put this artificial heart in you. They had one down in the lab. Denton Cooley never even put it in an animal, but he knew it was down there. And in point of fact, Haskell Karp wouldn't come off the heart-lung machine. They cut out his heart, sewed this device in. He survived on the device for 64 hours, but the valves were breaking his blood down, hemolysis. It was putting him in kidney failure, so they did a transplant. This was in April 1969, before we had good immunosuppression, and he tragically died 32 hours later of sepsis because they gave him so many steroids. So, very brave man, very brave family. Not the best outcome, but it was the first human to have an artificial heart. And if you play Trivial Pursuit, the answer to who put in the first artificial heart is Denton Cooley, not Michael DeBakey. That created this big feud between the two. For 40 years, they didn't speak. It was on the cover of Life. They made movies and TV shows about it. That actual original heart is enshrined in the Smithsonian Institute. You can go visit it, but its predecessors are still with us today. And they all work the same way. You have air hoses that tunnel through your body, and two pumps, because your heart's two pumps, right? One that takes the venous blood and pumps to your lungs. The other one takes the bright red blood returning back and pumps to your body. And each of those has an inlet valve and an outlet valve, and then bladders that fill with compressed air in this device. And as the compressed air comes in, it drives the blood out. If the air goes back out, it fills with blood. And this is a very nice way to pump blood. It's biomimicry, right? It's copying the way our hearts work. They inflate, they eject, they inflate, they eject. But it's got a real challenge. That device has been around now for 60 years. Remember the Jarvik 7 in the 1980s, Barney Clark? That was a direct descendant of this. Then other different brands. It's now called the Syncardia. It's the only artificial heart ever to be approved in the United States. But it's kind of tragically flawed. It's a brilliant device and has saved a lot of lives, but you have these air hoses through your chest. You wear this device on your back, which weighs 13 pounds, kind of heavy. And this device on your back wears out, but you can easily replace it, and they replace it every 3 months. The challenge is when this device wears out, and it does so capriciously, you instantly die. And let's do some quick heart math. If you're beating 100 times a minute, and that's what the Syncardia does, that's 1 million heartbeats a week, 52 million heartbeats a year. No man-made device can do that without breaking. And so it's a temporary device. It's just to keep you alive until you get a heart transplant. So it doesn't have an impact on the number of people that die of heart failure. It just changes who those lucky 4,000 or 5,000 patients are that get to live long enough to find a donor. Here's the results. We did have a patient that went 4 years on it and then died when his device broke. There have been capricious failures, so we leave them in for about 90 days while we frantically look for a donor heart. There are maybe 40 of these put in a year in the United States. Why? The stroke rate's very high, the infection rate's high. It filled an unfilled need and was an amazing device, but we need a better artificial heart. A lot of people have looked at it over the last 70 years, brilliant scientists. A group out of Abiomed in Danvers, Mass., recently acquired by Johnson & Johnson, but back in the 1990s said, maybe if we got rid of the external box and the air hose. They came up with this device. They spent $250 million developing it. It used silicon oil and internal clockwork to drive silicon oil back and forth, but the internal clockwork had hundreds of moving parts. It had flexible membranes that were flexing 100 times a minute. So it was a step forward, but not the right device. My partner, Bud Frazier, actually did 150 animal implants on that, and then they did a trial with 14 implants. The longest patient went 17 months before his device broke and he died. Only 4 of the patients lived longer than 9 months. And so even though that was kind of a brilliant technical solution, it was too big, it used too much power, it used 38 watts. Didn't balance the pulmonary and systemic circulation well. And then, of course, doing 1 million heartbeats a week, it wouldn't last. And that was the main problem. And so after spending $250 million, Abiomed pulled the plug on the project in 2004. Now there's another project ongoing that's trying to do almost the same thing as the BiVACOR, a self-contained beating device. It's called CARMAT. It's in Europe. It's very well funded. It's a complex device, lots of moving parts. It's big. It's a power hog. It beats 100 times a minute. They've had slightly better results. They've now done 100 implants in Europe. You haven't heard much about it in the United States because we only did 3, and when 2 of them capriciously failed and the patients died, the FDA said no more. So they went back to the drawing board. They're working really hard on it. In the first 40, 13 of the patients, a full third of them, died when the device failed. They've now gotten on top of that. They're doing a lot better, but there's still some capricious failures. I wish them well, but I think it is the most sophisticated airplane ever made with flapping wings. Sometimes biomimicry is not the best solution. So right now, if I ended my presentation and said, that's all I got, you wouldn't think too much about the future of artificial hearts. It doesn't seem too rosy, does it? But wait, a really interesting trend happened in the 80s. People said artificial hearts are going to be too hard, too many moving pieces, it's too challenging. What if we leave the heart in place and put a pump next to it, a left ventricular assist device? And I saw a lot of LVAD tech up in the meeting. Everybody started working on LVADs. And the first LVADs, again, Bud Frazier, as a younger man, worked indefatigably on them. And this was the first successful one. This is the first one that was commercial, that got approved by the FDA. It was about as big around as a coffee can. It went in your abdomen. There was a tube that stuck in the heart, in the weakened heart, and this would just assist the left side of the heart. Just downstream from that tube was a one-way heart valve, a tissue valve, and then it went to this can that had a pusher plate that was going 1 million times a week, and then another outlet valve and a graft hooked to the aorta. They thought, well, we're leaving the heart in, so when it fails, maybe we'll have time to scramble and do something. It was a big device. It was a heavy device. You can see here on the x-ray. And again, cyclic durability was its nemesis. It would last maybe 18 months, but it worked well enough that they said, we can do a study comparing this device to optimal medical therapy. And it won. So that was the birth of LVADs. But it lasted 18 months, and if you didn't find a transplant in that time period, you died. So that told us an assist pump could save lives, but we needed better assist pumps. And simple heart math again. So that's what my good friend Rich Wampler was thinking. He was on a missionary trip to Egypt, and he saw some workers using a shut-off to pump water up a riverbank. And a shut-off is basically a big Archimedes screw, and if you turn it, it acts like an escalator to move water against gravity. And Rich Wampler is one of the most brilliant scientists, engineers. He actually was an MD, but he never practiced. He said if it can move water against gravity, maybe it can move blood against pressure. So he made a shut-off, an Archimedes screw like that, very small, as big around as a pencil eraser, and he put it in a tube right back here and thought if I spun it fast enough, he could pull a meaningful amount of the blood out of the congested heart to improve the circulation and get them out of congestive failure. Well, this was 1981 he started working on this. There were no motors big enough, small enough, or powerful enough to turn this as fast as it needed to go. There are now, and this was, of course, the precursor of the modern Impella pump, Rich Wampler's genius idea. So there were no motors small enough or powerful enough that could go in the body. So he came up with the crazy idea of putting the motor on the patient's leg and having a spinning cable run up the leg artery, around the arch, and hooked to the device. And he showed it to my partner, Bud Frazier. And Bud Frazier famously said, "Well, that's the craziest thing I've ever seen. Let's try it." So they did cow after cow after cow, and it worked beautifully. And Bud Frazier famously said to Rich Wampler,
I don't understand why it's not breaking up the blood. You see, it's like putting fruit in a wearing blender.
And Rich Wampler explained, well, Dr. Frazier, you see, it's like running your hand through the flame of a candle. Your hand just sees the flame for an instant and then has all this trip through the body to recover. And the next time it may miss the candle. He said, oh, very good. So after doing a bunch of cows, they did it on a gravely ill patient. They didn't have to wait long for the right patient at the Texas Heart Institute. It was a 58-year-old man who'd had a heart transplant 6 months earlier. This is now in the era of heart transplantation. We'd figured out immunosuppression. He came back in florid heart failure. His lips were blue. His lungs were filled with fluid. He wasn't making any urine. He was going to die right then and there. They took him to the operating room, slid this thing across his aortic valve, up his leg artery, under x-ray, turned it on, and while they watched, in 3 minutes, his lips turned pink. He started peeing gallons of urine with the new cardiac output, and within a day, his x-ray cleared up. He was extubated. Tragically, 2 days later, the cable broke, but by then they'd started OKT3, a new anti-rejection medicine. His heart started back up. He was discharged home 10 days later and lived another decade. And here he is, this very brave patient in 1988, an amazing milestone, the first human to have a rapidly spinning thing in his body. And they had a press conference, and there were tons of people at the press conference. And Bud Frazier presented the patient, and the patient was there. And someone in the back goes, Dr. Frazier, that's a great milestone. He said, well, thank you. We couldn't have done it without Rich. It was a bit of a shoestring catch. And he goes, yeah, why doesn't the pump, you said it spins 2,700 times a minute? And Dr. Frazier said, oh, that's right. He goes, why doesn't it break up the red blood cells? And Bud said, well, you see, it's like running your hand through the... Anyway, everybody was very congratulatory. They all leave. And Rich Wampler famously came up to Bud Frazier and said, Dr. Frazier, great job. He goes, oh, thanks, Rich. We couldn't have done it without you. And he goes, one correction. He goes, huh? He said, you said it spins 2,700 times a minute? You know, it's actually 27,000 times a minute. And Bud looked at his shoes and said, well, I guess it's a good thing I didn't know that. I never would have tried it. Anyway, so fortune favors the brave. Anyway, that gave rise to all these spinning pumps, some of which I saw models of upstairs, some that Paul tests in his lab, and they're all sort of the same. They have a rapidly spinning member. This was the first wildly successful clinical one. This is the HeartMate 2, one moving part, suspended by gemstone bearings. They said you couldn't have bearings in the blood, but the blood rushed over them so fast it kept them cool, kept them washed. And there are patients that have had some of these for over 20 years. The very first one of these, placed at the Texas Heart Institute, about 3 months after I came back down from Harvard and joined Bud Frazier in a 17-year-old boy after doing 2 cows with it. They'd done the GLPs in Pennsylvania. Anyway, look how much smaller this device is. Instead of tons of moving parts, it's got one, no flexible membranes, no valves. It used a lot less power and much better durability. As I said, there's one patient now who's 22 years out in San Diego. Bud has one that's 20 years out, and over 500 patients have had one of these for 15 years. It's changed the whole world of mechanical circulatory support. And these are all pumps that came out, and I show this slide because all of these are now obsolete. But there are tons of new ones, and new ones are coming out all the time. So that fundamentally changed the field, and that's why I left Boston and came back down to Houston, because Bud Frazier said, hey, Billy, why don't we leverage these little pumps to reinvent the artificial heart? And I thought that sounded like a great idea. My mom had just left Houston and moved up to Boston to be near us. I said, bye, Mom, I'm going back down to Houston. Couldn't have worked out worse, but anyway. Rob Jarvik, you've heard of the Jarvik heart, and Rob Jarvik had switched his focus to a rapidly spinning turbine. He made these little turbines, and he did all his training at Texas Heart, had trained surgeons how to put his pump in. So he loaned us 2 of these, gave us 2 of them. They were like $80,000 each. We took a cow, we opened him up, we went on cardiopulmonary bypass, we cut his heart out, we put 1 turbine in the left atrium, 1 turbine in the right atrium, hooked the right atrium one to the pulmonary artery, the left atrium one to the aorta, and then took this great x-ray showing flow going through the lungs, coming back to the left atrium and going through the aorta. And we said, man, that's great. That's real progress. But the surgical field looked dry. We had approved the animal study for a chronic study. This wasn't supposed to be chronic, but I said, let's just close them up and take them over to the ICU. And everybody started complaining that it was a waste of resource. I said, let's just see what happens. What's the harm of it? We wire them shut, we take them on the stanchion and roll them in the ICU. I go upstairs to answer some emails. 3 hours later, they said, hey man, you better come down to the lab. Here's that animal standing up, eating hay. No heartbeat, no pulse. His whole heart is just 2 turbines. His heart had 2 moving parts. And we said, Tin Man, shout out to the Wizard of Oz. We thought, oh my God, this is really something. And we started getting money and grants and stuff and did it over and over again. In fact, with that animal only went 21 days. It stood up in its stanchion. One of the controllers fell off and disconnected. But we were really eager to do more. We used these same 2 turbines and 2 more animals. They were getting kind of gross, and one of the drive lines got cut when we were taking them out after the 3rd. Luckily, Michael DeBakey had started a turbine company in Houston called Micromed. It's no longer around, but I became the chief medical officer of that so I could have access to their pumps, and started doing a lot of twin Micromed turbine animals. Now, it wasn't configured like a little bullet that you could put in the left atrium and the right atrium, so we had to do some engineering. Remember who MacGyver was? You know, you could repurpose things that were readily available in his environment to defeat nuclear war, terrorists, and defuse nuclear warheads. So I went to the fabric store and got some Dacron polyester. I took a styrofoam cone from Hobby Lobby and sewed it around it, and then went to medical device prototyping headquarters and got drywall tape, the stuff you put on drywall before you paint it so you can't see where the seams are, and bath and tile caulk, the stuff you put around a toilet so the water doesn't leak down onto the kitchen sink and downstairs. And with that, sort of piñated these things together. So I made these little adapters that were soft and squishy enough that they could accommodate the geometry, the anatomy. You could cut them and they wouldn't fray. You could sew through them and the needle holes wouldn't tear and didn't bleed because of the silicone. And on the inside was a beautiful sheet of Dacron polyester, which DeBakey had taught us in the 60s you could put in the bloodstream. And with these, we'd take a cow to the operating room. We'd go on bypass. We'd cut the heart out. We'd sew one of those to the right atrial remnant and put a turbine on it, a second one to the left atrial remnant. We then would cross those, so the right atrium went to the PA and the left atrium went to the aorta. And there's that cow, 7 weeks later, walking on a treadmill. There's the late, great Denton Cooley. There's Bud Frazier. I'm holding the molasses. We were just blown away. And we thought, this is the future of the artificial heart, because it would never wear out. It was so much smaller. It used so much less energy. There's our device next to the BiVACOR, the one they spent $250 million on before they gave up. We did it with HeartMate 3s. We did it with HeartWares. In fact, here's a summary of our 68 animals that we did. And this is very labor intensive and takes a lot of money, but we were getting grants and keeping it alive. We would cut the whole heart out. I showed you what we did. Only 3 of the animals went 90 days. Infection was a real problem because they'd go to the bathroom and then lie in it. And we had great animal techs and stuff, but it's a really, really challenging prep. Only 30 of them went longer than a week, and only 8 of them were able to walk on a treadmill. But we thought this shows great promise. One of the challenges, you had 2 controllers for the 2 pumps. We had a project going to try to get the controllers to talk to each other, but never really finished with that, but that was one opportunity. The biggest problem was right pump thrombus. We all form clots in the veins in our legs, and they break off and go through our heart and go to our lungs, and our lungs filter them out. You get a pain in your side, you cough a little bit, it bugs you for 2 or 3 days, and then you don't think about it anymore. How do we know that? Autopsies of young, healthy people that die from trauma or in battle have little scars all over the place from pulmonary emboli. But one little clot will take out one of these pumps because they have such narrow gaps. In fact, 1/3 of the animals, the experiment terminated when a clot went into the right pump. This is sort of what it looks like. But still, we thought, well, 2/3 of them didn't have that. And so Bud Frazier said, look, This is smaller than previous devices. It uses less power. It's going to be very durable. We should probably try doing this on a patient that has no other option. And this was a basic ask for forgiveness, not permission. The pumps had just been approved in 2010. It was now the 2011. So we waited. We knew, though, if we sewed drywall tape and bath and tile caulk into a patient, we would go to prison and lose our medical licenses. So that wasn't appealing. But we found stuff on the shelves of the Texas Heart Institute that were similar to drywall tape and bath and tile caulk, specifically hernia mesh. Instead of $5.99 for a 25-foot roll, it's $2,000 a sheet. The cardiovascular barred cardiovascular patch, Dacron polyester, just like I was getting at the fabric store. Instead of $21 for a square yard, it's again $1,000 a sheet. And then NuSil medical silicone that they use to cap off the screws in pacemakers and AICDs after you tighten the nut. And with that, made the world's first continuous flow total artificial heart, where everything in that picture is approved for implantation, albeit perhaps not in that exact configuration. We did 2 cows with that, showed it worked great, and then waited for the right patient. Here's the world's first human being with a continuous flow artificial heart. This was in 2011, 6 months after the HeartMate 2 got approved. He had cardiac amyloid. This rogue protein had infiltrated his heart. His heart was barely beating. He was on ECMO. He had liver failure, kidney failure. He was on dialysis. He was trached and pegged. He was going to die. We had given up. But we thought if our device could give him reasonable hemodynamics and he could exercise, maybe he could go to MD Anderson and get a bone marrow transplant, and then we consider doing a heart, liver, kidney transplant on him. And so we did the implant, and he woke up and got extubated 2 days later. So here he is. You can see how yellow he is. He's very jaundiced. He's on dialysis. He was an engineer. You can see there he's working on his laptop and drawing us pictures of control algorithms to help the 2 pumps talk. He was an amazing, amazing, and very brave man, Craig Lewis, 52-year-old engineer. Tragically, over the next 4 or 5 weeks, his liver enzymes continued to rise to the point where he couldn't maintain wakefulness. He became very somnolent. His family had a meeting and asked that we turn him off, especially because he started coughing up blood. We bronched him, and he had amyloid in his lungs, so it was just a bridge too far. And so after extensive discussions, we turned the pumps off and allowed him to pass. Very brave man, very brave family. We got some great publications out of it. Bud and I got to go to Lincoln Center and do a TED Talk. We were featured in a lot of lay press. When I was a little boy, I was an uber science nerd. I subscribed to Popular Science. The first subscription, you got me, Mom, and I used to wait for it to come in the mailbox. And I would just pore over every page and every ad. So when we showed up on the cover of Popular Science, I said, time to go home and wait for a happy death. I'm done. But the most important thing that came out of this is we met this incredible young man, young at the time, not so much now. This is 2011. This is Daniel Timms, who in his PhD studies, while his father was dying of heart failure, came up with a continuous flow idea for an artificial heart. He didn't know what we were working on. We didn't know what he was working on. He lived in Brisbane, Australia. Everybody he showed it to said, "Kid, you're a nut. Get out of my office." He was out of money. He saw that Bud Frazier and I were working on this. He said, it's worth a shot. Flew to Houston on his own dime. I had him on my calendar for a 30-minute visit. 6 hours into that 30-minute visit, I was saying, you're not leaving Houston. How much money do you need? We're going to make this happen. He said, well, if you come up with $2.5 million, I can bring the team here for 18 months. The team was in Aachen, Germany. There were several of them in Australia. There were several in South America. And he said, I think we can actually make this pump. It was more of a concept. He'd never done an animal. We knocked on one door. Mattress Mac, very famous Houston philanthropist and furniture salesman. And a week later, we had the check for $2.5 million, and Daniel brought the team down. This brilliant team is still together now, 14 years later. They're all still part of the team. They're all now the senior members, where some of them were still working on their PhDs when they came down. And I was on their thesis defense for some of them. This is the device that ultimately we made. It has exactly one moving part, and the one moving part is suspended in an electromagnetic field. It's a double-sided impeller. That side that we're looking at now takes the red blood and pumps it to the body. Those tall Stonehenge-looking things take the venous blood and pump it to the lungs. There's a brushless DC motor, microprocessor commutated, that makes it spin. So there's the brushless DC motor, 12 electromagnets, 3-phase groups of 4. And then there's 3 electromagnets on the other surface that are adjusting 2,000 times a second, and eddy current sensors that are measuring the position of the impeller 20,000 times a second to keep that piece floating in an electromagnetic field. It never touches. And because we cut the big disease heart out, we've got so much more room for this. Our gaps are huge. It's blood friendly. It doesn't break blood. It doesn't consume von Willebrand factor. And we know with absolute certainty that one moving part never touches anything. Well, how do you design something like that? Well, in the modern world, everything exists as a SolidWorks file, a digital file. So we could iterate on a daily basis because CFD, computational flow dynamics, will only get you so far. Garbage in, garbage out. You got to do the test on the bench. So we would print literally hundreds of left-sided rotors, and right-sided rotors. These are right-sided impellers, and these are left-sided impellers. And if you look at those all in the front, they look similar, but real subtle differences. How high the blades are, how much backswept angle, how many of them there are, what the curvature is, had dramatic impact on how they would perform. Similarly, the volutes, and there's some left-sided volutes at the bottom and some right-sided volutes. Subtle differences in the breakwater or the spacing or the axisymmetry had dramatic impact on function. And so we had all these parts and we thought, well, how are we going to test all these? One of the engineers stepped up and said, look, I made an automated tester, semi-automated, put a volute in and a rotor, and it'll run through using a pneumatic sort of pinch valve every afterload at every speed and at every spacing. That's a micrometer on the end because this impeller, this spinning thing, could drift to the left or right and did that several thousand times a second to balance the systemic and pulmonary circuit. Well, if we're making it so that the impeller performs differently depending on where it is, we got to check every spacing. But this thing generated all this data and then looked through, generated all these curves. Here's one rotor in one volute at different pressures and flows at 1, 2, 3, 4, 5 different spacings. So we had about 1,000 graphs like that, and then used software to go through, and the software said, okay, that's your best right-sided impeller, that's your best left-sided impeller. That took a month. So we said, well, let's see if it's right. We actually 3D printed a plastic heart. You can see below the surface right here, this is the motor. You can see through this thin plastic. It had to be really thin for the electromagnetic force to be transmitted. And under here you can see the 3 electromagnets that keep it balanced. And here are the 3 eddy current sensors. And there on our impeller is the best right-sided blades and the best left-sided blades. And there was our completed 3D plastic heart. And we said, well, look how much smaller it is than an BiVACOR. It's got one moving part instead of 350 moving parts and no flexible components and no valves. It allowed us to do hemolysis tests. And here you can see our BiVACOR pump performs at 12 liters, about like a HeartMate 3, which is the overall class leader. So we do at 12 liters what it does at 5 liters. So the best hemolysis in the field. Why? Because we cut out the diseased heart. We've got so much more room. Our gaps are so much bigger. It also allowed us to characterize hydraulic function and hemodynamic performance. And we did all that. We said, this thing works great. And then Daniel says, well, let's sew it in an animal. I said, Daniel, you can't. I mean, this is a 3D piece of plastic. Won't it warp? And he said, yeah, after a while, but let's see how it does. There's the 3D plastic pump sewed into a cow. Those light blue things are flow sensors on the aorta and pulmonary artery. And there's that cow eating, acting like a normal cow. Now, we could only go 1 to 3 days with these because the plastic was hygroscopic. It soaked fluid and it would warp, and it had to be very precision flat. But it told us that we had the right hydraulic performance. And this cow has one moving part, no heartbeat, no pulse. But then a lot of people started saying, you can't have a pulseless artificial heart. And I'd say, well, why not? Well, mammals need a pulse. Well, have you ever seen a bird soar in a breeze without flapping its wings? You know, and airplanes don't have flapping wings. Why do we need a pulse? At the capillaries, nobody's got a pulse. If you use confocal microscopy on your capillaries, the red cells go through one at a time with no cyclic variability. And those 68 animals we did, they didn't have a pulse, and they did okay. You could argue that only a couple of them went 3 months. But we know if you have a blocked artery, like a 60% carotid, and you put one of these spinning VADs in, if you don't have much of a pulse left, they're at increased risk for thrombosing that and having a massive stroke. Or if it's a 50% in their popliteal artery, they'll come in with a cold leg. We know that a third of the patients with GI bleeding, with LVADs, have GI bleeding, and that may be due to lack of pulsatility. There's a lot of research that's going on. And a pulse will certainly help us wash out the device. The flow through the pump will be changing every time we do a pulse. So creating a pulse may be of some merit. Well, this is a digital pump. We can make any waveform we want. In fact, we now have it so it makes a dichrotic notch, so it looks like a regular arterial waveform, just by speeding up and slowing down. And if we do a 900 RPM cyclic variation in the speed, so you set it at 2,000, it goes up to 2,600, then drops to 1,700 once a second, so your heart rate is 60.000. And here it is pulsing. You feel it. You put your fingers on the graph, and you can feel the pulse. You can see the pulse. There's an animal with a pulse. Look at this arterial waveform. You can barely see it on this screen, but you got to take my word for it. It looks like a regular arterial waveform. And if you say, people, is that a magnetically levitated rotating disc that's spinning fast and slow? People say, no, you're faking it. But it's real. This pulse, you can feel it at the wrist, you feel it at the carotid. A pulse oximeter picks up and tells you what their saturations are, and they can go to Walgreens and put their arm in the blood pressure cuff, and it gives them an accurate blood pressure. So now we had the design down. We needed something more durable. We did selective laser sintering. This allows you to print in metal. These are 30-micron titanium spheres and a laser looking at our computer file, melting them together. It does that all night long, puts down another layer of beads, another layer of lasering. You then have to put a hazmat suit on and a respirator, because if you breathe this titanium dust, it'll kill you. You brush it off, and there, rising like Venus from the mist, is the first titanium BiVACOR heart. We were super excited. Here we are implanting it. There you can see Rich Wampler. We call him Captain Hemo, the guy who made the first continuous flow pump. Rob Jarvik came to some of these. There's our whole team. Over here is the whole BiVACOR team, all there waiting in great apprehension. And I got to say, a tip of the hat to the Texas Heart team. We built this amazing organization of veterinarians, animal techs, engineers, the BiVACOR team. It takes this kind of team to do this kind of work. That's Gil Costas, our veterinarian. There, Daniel and Nick Graytrex. That's Kelly Harm. She rides with the animals as we come out of the OR in the stanchion to make sure nothing gets tugged. It takes a lot of resources, a lot of time, a lot of energy, and a lot of money to do this kind of work. But we were in it to win it. Here's an animal at 2 months walking on a treadmill with a BiVACOR heart in pulsatile mode. We got pretty confident. We knew what we were doing. We were at design freeze. We had animals that would go 3 months. They put on 80 pounds of lean beef in 3 months. And having a cow that big in an animal lab that's in the basement of a hospital is not a trivial issue. But at that point, we thought, listen, we've got this figured out. So his cardiac output would go up like 4 or 5 liters a minute while he was exercising. We did design for manufacturing, like the kind of stuff you guys are talking about, so we could make this. It's made out of 7 different pieces, all that are now hogged from titanium, because the FDA has no way to figure out about 3D printed titanium. They will someday. They're doing it in orthopedics. It's just a matter of time. We'll be ready for them. But right now, it's cheaper and easier to hog it out of billet in 7 different pieces that are laser welded and then polished, and the motors are potted in epoxy. In 2022, we'd done 40 chronic animals at that point and a ton of acute animals. We approached the FDA. We had great interactions with them. Our lead reviewer, Eric Richardson, used to be an engineer on that BiVACOR heart. He loved the field and was super helpful and just the best lead reviewer in the world. He said, we want 5 animals for 90 days. We arm wrestled with him and said, look, this is a hard prep. And he said, well, the LVADs had to do that. And I go, yeah, but you leave the heart in an LVAD. We reached the decision, 5 animals for 30 days. Here they are, 5 in a row. They weren't on Coumadin. They weren't on aspirin. They weren't on anything. It's really hard to get Coumadin to work in a cow because they've got 4 stomachs, and aspirin doesn't work on them at all, so we did the best we could. There were some things they saw, clot on the central line with some emboli to the lungs in one animal. A lot of them got infections. They asked a bunch of questions. We went back into our older data and showed them histology because we'd gotten histology on all 40 animals. And finally, and they said, well, before you do it, you need durability. This is Huntington Beach, California, where the company is now located. We have 8 pumps that are approaching 3 years of constant function without a failure. And at that point, we had over 6 months, which is what they wanted to see before we did EFS. This is our system as it now exists. You've got this little briefcase type thing that weighs about 6.5 pounds, and you've got a drive line that goes through your skin, and you replace batteries every 8 hours or so. So it's not our ultimate concept. This is more of our right flyer, but good enough to see if we can take people up for a flight. There's a little iPad that you can hook up to it so you can program the device and read data out. Our ambition is to get rid of that box. You see the box on the first one. We now can, in the modern world, you can take electronics and make them very small. Anyone with an iWatch or an iPhone knows that. We've now done that. We have a pump where all the electronics are actually in the can, in here. And this box has gotten very small. It's now just the batteries, which takes us to a wireless system. We're only consuming 10 watts for 10 liters a minute, not like the old ones, so we can do transcutaneous energy transfer, and we're already partnering with some of the people out there that are developing systems. So when we have a wireless system where all you have to do is change your batteries, we think we may be able to compete with heart transplantation because no immunosuppressants. Heart transplants, mortality a decade is about 40%, so 60% are alive at 10 years. We think we can beat that. Well, in November of 2023, they got back to us and said, okay, you can start human trials, you can do an EFS, you can do 5 patients. The patients have to stay in the intensive care unit after they get the device, and then once they're healthy enough, if they survive the operation, relist them and they'll get transplanted. We said, great. We went to 9 different sites. The first 4 to activate were the Texas Heart Institute, where I still practice, Banner in Phoenix, where Francisco Arabia, a leader with the Syncardia heart, the older one that I showed you, Christ in Cincinnati, where Rob Dowling, who did a lot of the BiVACOR hearts, and then Duke, which is one of the busiest LVAD centers. And getting these sites activated was a Herculean task. The whole team had to come to Houston and do animals with us and cadavers, and then we had to go to their hospital and train their perfusionists, their critical care doctors, their nurses, their perfusionists, the surgeons, of course, and then going through the legal thing with the hospital, getting insurance, indemnities, subject to injury language, clinical trial agreement. That took us 6 months, but in June we were ready. And we were making pumps 1 a month, so here's our implants on July, August, 2 on August, October, and November. These are the first 5 patients implanted in the United States. All of them lived to be transplanted. All of them are home with their families, doing great. Each one of these was on their deathbed when we took them to the operating room. 4 of the 5 had an Impella 5.5 in and were going into right heart failure. All of them were 10 to 20 kilos up from right heart failure, and they were trying to decide what to do with them. None of them were LVAD candidates because they had biventricular failure. In each case, these patients were extubated on day 2 or 3. And each day they were up walking in the halls on day 3 or 4, and you can see some of these patients were walking over a mile a day in the hospital while they were waiting for their heart. It was a double-edged sword. It worked so beautifully, but they were relisted so quickly. You can see some of the durations of support were very short. The last one at Texas Heart was only 5 days before he was up walking in the hall. And once they listed him, since they were unistatus 1, they were the sickest patients, they had an experimental device, they got a heart right away. So we were very pleased with this, that they all survived. And one of the reasons they survived so well is the cardiac output this device produces has never been seen in the field. With an LVAD, you can get about 6 or 7 liters a minute. These patients, when they walked, would have cardiac outputs of 13 to 14 liters a minute and CVPs in the single digit. Still, we were very pleased. But while the FDA was ruminating on this, we went to Australia on November 22nd and implanted one in a gravely ill patient at St. Vincent's Hospital in Sydney. He's the first patient we sent home with the device. He came back in 105 days later and got his transplant, and he's now home as well. This is what the device looks like in a human chest. I still get a thrill when I see this after 20 years of work. It's kind of like, yeah, man, we're doing it. Here's a patient on day 12. This patient was on his deathbed with an Impella 5.5. Here he is on post-op day 8. On post-op day 12, he did a 420-meter, 6-minute walk. So with LVADs, if you can do a 400-meter, 6-minute walk at 4 months, that's associated with good prognosis. If you can't, it's associated with bad prognosis. 1/3 of LVAD patients can't do that at 4 months. He did it at 12 days, and this guy was in cardiogenic shock with an ECMO. It's really rewarding. At 27 days, that patient went 27 days before we got a transplant. He was a big guy. We needed a big heart. We took the device, we filled it full of saline and dumped it out, and then put a boroscope in, and that device looks like it just came off the factory floor. No galling, meaning no metal touch metal, not a drop of blood, not a piece of clot. Very, very exciting, very rewarding to see. That's why we think this thing is going to go a decade or more. They've just approved, the FDA has just approved us for 15 more cases. We have held off in starting them until we get approval, hopefully tomorrow, to send the patients home while they're waiting for a heart transplant. That way, it's unistatus 2, not unistatus 1, so they have to wait a lot longer for a donor heart. And it's 2 separate DRGs, one where they come in and get the BiVACOR, and then another one when they come in to get their transplant. 2 separate bills. We'll be able to bill for our device. We got CMS Category B. We just got back from Melbourne where we did site activation there. They're screening patients. We're getting calls about patients, but waiting for good pitches over the plate because we want our data to be good. We pick good doctors and good hospitals. We want to pick good patients in our first series. We have 6 pumps ready to go. Once this letter comes in, we'll probably be back and implanting in June, and we'll probably be doing 2 a month or 3 a month. This is our Australian patient working out. He was going to the market. He was washing his car. He was living like a normal dude. Nobody knew he had an artificial heart. And like I said, he did great. And he wasn't taking his Coumadin like he was supposed to, but he still did fine. There's our first patient. He came back. We had a thing at the Texas Heart Institute with the board of directors of BiVACOR. You know, making money, raising money is a big part of MedTech, and coming up with the right materials for that and storytelling is a big part of that. And it's a challenge. We're now doing a $90 million round for anybody who's got a checkbook. So we've got a long way to go, but the first 5 went great. We got 15 more to go. The PMA, we wanted to do a long and short trial with the FDA, like HeartMate 3 did. They said, no, do bridge to transplant first. At first we were despondent because we really want to get to destination, but then we realized it was a blessing in disguise because now we can start it a lot earlier. We don't need the long biocompatibility and extractables and leachables, so we're getting ready to start that up now. They also told us these 15 EFS, a lot of those can count as patients in our pivotal, which is great. I never heard of that before. We've just gotten back from Taiwan and Japan and Australia. I told you we just activated the Royal Alfred in Melbourne. Taiwan, We're really keen to start there. They have tons of patients on the transplant list, 1,900 right now. They do 90 transplants a year. We'll get much longer implant times. They're super keen to get involved. They're coming to Houston May 20th, and we've got an animal lab set up. Like I said, we want to be UNO-status 2 so we can get longer-term data. I think continuous flow blood pumps are super well suited for making artificial hearts. We can get a pulse. They're smaller, less mechanistic complexity. They use a lot less power. I think this is going to be the first permanent artificial heart in the world. And I think someday we may replace transplantation, someday in the not too distant future. And so I thank you for your attention. This has been a Grail Quest. It's been great fun, and I enjoy talking about it. If you'll indulge me, can I show one more slide? Yeah, so I was Michael DeBakey's last chief resident, and then I went to Harvard for 11 years, and then I came back and joined Denton Cooley's group. And these two great men, you know, separated by a parking lot, but they never spoke. And it just bothered everybody. And since Bud Frazier and I both trained with Dr. DeBakey, we would go over at night and we'd show him what we were working on when we were doing the dual turbines and stuff. And he'd say, "Oh, you see," I learned to imitate all these guys. "Well, you see, it's very satisfying seeing somebody work on this. I thought of this years ago." You know, hallmark of a good idea, as everybody's had it before you. But we would invite him to come over to the Texas Heart. Of course, he'd never been to the Texas Heart, but we'd say, "Come over to a lab. We're putting one in a cow tomorrow." And always, for some reason or another, he couldn't come. But then one night, Bud Frazier goes and talks to him. And he says, "Well, I'm going to tell Henny. We'll try to make it over." So that morning, and Bud didn't tell me, I'm in there getting the cow ready, messing with my headlight, my camera, and the phone rings, and they go, "Billy, it's Dr. George Noon." George Noon was one of Dr. DeBakey's close associates. And I go, "Hello?" He goes, "Hey, Billy, it's George. We're coming over in the hall to watch the implant." I go, "Who?" He goes, "Dr. DeBakey, me and our group." I go, "Oh." So I called Dr. DeBakey. He goes, "Yeah, he said he was going to come." He calls Denton Cooley. That day, we take this picture. In this picture is Matthias Lobe, a renowned German surgeon. Here's me putting the pump in. Here's Bud Frazier getting in my way. Here's George Noon. Here's Michael DeBakey and Denton Cooley sitting and just chatting like they've been best friends the whole time. They talked, they were laughing. They were making too much noise. Actually, I didn't want to tell them to be quiet. But shortly after that, Dr. Cooley invited DeBakey to join the Cooley Society. DeBakey invited Cooley to join the DeBakey Society. DeBakey found out he was going to get the Congressional Gold Medal. He invited Cooley to Washington, D.C. for the ceremony. And so I think a device like I just showed you not only has the potential to cure a lot of the challenges of end-stage heart failure, but it can mend badly fractured relationships. Thank you very much.
Well, Billy, not surprisingly, that was phenomenal.
Thanks.
It really brought us through the whole innovation process of a device and how hard work it really is. It was also very entertaining. This is the true renaissance, man.
And I'm a part of a big team, and I did 3% of the work.
Yeah, well,
anyway.
He's a renaissance man. He plays in a band. He's an amazing musician. He just told me he built a remote-controlled BMW so his dog could drive. But with that, we have time for a few questions. So anybody from the audience have a question?
Mom? No. Somebody ask a question, I'll be really embarrassed. Yeah. Are we going to do anything for infants? Great question. And I presented at the ACTION meeting, which is the Pediatric Consortium at the International Society of Heart and Lung Transplantation about 48 hours ago. And several of the world's most prominent pediatric surgeons, Chuck Frazier, Iki Adachi, David Morales, have been down to Houston and done 25-kilo sheep, which even though 25 kilos is big for a baby, but they have a weird-shaped thorax, so it's almost baby-like. We think we can do like a 7 or 8-year-old. The space between the posterior sternum and the T10 vertebrae for all these devices is 14 or 16 millimeters. We're 8. So yes, We don't think it's going to be good for a neonate. I think they'll still need a human heart transplant, but when that organ wears out, we'll put a BiVACOR in for a decade or two so they don't have to have 3 transplants. And could we design this over again to make it the size of a Dunkin' Yo-Yo or smaller? Yes, but we would have to redesign every aspect of it. And but that's something maybe we'll do, because it could be life-saving. There's a palpable unmet need. Berlin Heart is a great device, that pericorporeal, and they've done a lot of great stuff for gravely ill kids, but we're looking at that. Great question. Yeah, Art.
Yes, thank you. Wonderful presentation again. As you're ramping up for lots of applications, are you able to automate the manufacturing process for the titanium housing at all? Or is it onesie, twosie?
So, I mean, you're exactly right. Everything can be automated. And you say, oh, no, it's incredible precision. That doesn't matter. And that's just an economic decision. But when we start making a lot, we'll bring in people and try to figure out what we can. It's just hogging out billet. You know, and I don't think there's much more precision in that than in a Tesla. You know, I mean, it's got to be flat, but so do a lot of components of a Tesla. So at some point, I really look forward to the day when we're having those kind of discussions. We're ambitiously going to where we're going to be making 5 pumps a month by the end of 2025. And we have a schedule that we're trying to tell our investors that we're going to keep to, about a cadence of implantation and when we're going to finish this bridge to transplant study. The bridge to transplant study, by the way, starts Q2 next year, because we think we're going to bang through these 15 faster than those 5. Those 5 we did, we were only making 1 pump a month, so we can only implant 1 pump a month. The number of patients presented to us to implant were 3 times that, and we had to just say, sorry, do something else on them. We don't have a heart. And so that was with 4 sites. When we opened to 15 sites, and at this event that we had yesterday, we had a breakfast, no, it was today, we had a breakfast in Boston at the International Heart and Lung Transplant Society, and there were 37 heart surgeons that showed up, and they all want to implant the device. Anyway, great question.
Hi, over here to the left. Kimberly Gustafson here in mechanical engineering at the University of Minnesota. I'm curious to know if you're optimistic about the power source being able to be fully implantable, and if you think that's necessary for achieving your goal of replacing heart transplants.
Yeah, that'd be really, really nice. And very ambitious right now. But you know Moore's Law? You know, every 18 months things get faster, smaller, cheaper, et cetera, et cetera. Do you know Cole's Law? It's ground up cabbage, salt and pepper. It's good with fried chicken. Sorry. Low-hanging fruit. So battery technology follows its own ramp and always has. And it's because of cell phones and electric cars. They've gotten safer. They've gotten more power dense. And we're counting on that continuing to happen. When will it happen to a point where you can put a battery in the body? I don't know. Right now, our main problem is hysteresis, because you can charge a battery percutaneously with inductive coupling, but after every charge cycle and drain cycle, it becomes less effective. And now we'd have to take the patient to the operating room every 3 years and replace the battery. Is that maybe what we're going to do? Who knows? There are test systems where the batteries are outside the body, but you have no drive line. And there are some people making those, and they all want to take us to the prom. And so we're meeting with those, and we've done some experiments, and it's very encouraging. But yeah, if a nuclear battery, they had nuclear batteries in the 70s that would do 50 watt hours. But a bunch of people walking around with fissionable material in their bodies in today's geopolitical climate's probably not a great idea.
Hi, Dr. Cohn. First, it's a huge gift to have you here today. It's always a pleasure to hear from you, so thanks for sharing the story. This question is around your estimate for the timing of moving from bridge to transplant to destination therapy. And one facet I'd love for you to share on your estimate here is, how do you see the impact of normothermic regional perfusion and donation after circulatory death impeding the timing toward DT?
Yeah, so he's talking about now, historically, you would take a patient who was brain dead, and after getting all the family together and agreeing, you would take that patient whose heart was still beating vigorously to the operating room and take the heart out, pack it nice, and get in a jet and fly back to your hospital and implant it. Now we know that you can take a patient and wait for them to die, and then wait 5 minutes by your watch and dive in and take the heart and resuscitate it. We have these organ procurement boxes that do normal thermic regional perfusion. You get the heart banging again, and now you've got a lot more time to get it in the patient, and they do it with the kidneys and liver and the gut, and it's really changed the field. So the donor pool is expanding. Heretofore previously, before all these technologies, it was fewer than 4,000, and I think this last year it was almost 5,000. It's going to continue to climb, and that's a great, great thing, but it's still a fraction of the amount of organs we need. So I think, is that going to impact the application and need for a heart replacement device if we make an attractive one? I don't think so. I think patients will have to consider choices, but it'd be nice to have another choice. And if we end up doing only 4,000 or 5,000 a year, we'd be delighted. If we do 100,000 a year, that'd be even cooler. So yeah, and a lot of technology, these organ procurement boxes at the ISHLT, which is going on right now, I was there yesterday, there were now 5 different companies, the Sherpa, the Transmedics, and we have one at Baylor College of Medicine that Gabe Luer is doing. Do you know Gabe? Anyway, so yeah, my dad taught me the only thing you can count on in life is change, except from a vending machine. We just need to stay ahead of it and keep innovating and provide something that's of value and helps patients. Yes, sir.
Thank you so much for everything you've done, setting up these next generation of innovators to take the next steps. I'm going to simultaneously be an optimist and a realist, having studied delivery of healthcare around the world. Amazing clearing of technical and medical hurdles. Ultimately, the last hurdle becomes affordability. I'm curious what challenge you might give to other people, or what you see as the remaining hurdles to bring this to the millions who need it, really scaling it up in the future.
Sure, that's a great question, and right at the center of what we're thinking about. It's right now so expensive to make each one of these, and we're trying to recoup our losses, primarily because in the real world, we have to appeal to the investment community, and they have to say, they have dollar signs in their eyes. And so we had a regulatory reimbursement consultant, Tina Ivovic, who some of you may know, and she did an analysis where they said, yeah, so ordinarily they put in 2 of these LVADs, and the results with that are just terrible, and that would be $150,000 each. You can justify selling this for $300,000. And the BiVACOR sold for $900,000 on the Carmet. So that's what we're going with. And a lot of people, we tell them that, and they go, you'll never get that. Well, we had a conversation a week and a half ago with Jay Gomez, who's the Chief Financial Officer of Baylor St. Luke's Medical Center. And we were talking about it, and Tina was on the line, and we said, well, he says, what are we going to, because we were talking about how we're going to do this trial where we send the patients home, 2 different DRGs, and we're going to bill for the device, and we'd had to do a new clinical trial agreement for that and go back through the IRB. He said, well, what's it going to cost? And I said, are you sitting down? He goes, yeah. And I said, $300,000? He goes, oh, I thought you were going to say a lot higher. I thought you were going to say $900,000. I go, damn it. And it reminds me of Colonel Tom Parker, who used to manage Elvis Presley. They would go to a small town where they were going to put on a show, and the mayor of the city would say, you know, we're just really excited about having Elvis here, and everybody's all pumped up. He's going to be the centerpiece of our whole festival, and we really want to do it. What's it going to cost? And Tom Parker would kind of measure the guy up and look at the city and see how nice it was, and he'd go, $75,000. And if the guy said, great, let's do it, then he'd go, now we got to talk about Elvis's fee, you know. So anyway. So yeah, is it going to get cheaper? And is it going to affect more than just the first world? Ambitiously, yes, but it's going to take iteration. It's going to take better design for manufacturing. Every technology gets cheaper and easier. When we bring in automation and make it out of cheaper materials and replace some of the titanium with plastic, who knows? I mean, this cell phone, this very cell phone, in 1990 would have cost $100 million, you know? So that's what technology does. So we would love to make a difference, and to do that, we've got to disseminate the technology.
One last question. Nope.
Yeah, this is something I was thinking about with diminishing returns on the hysteresis of the power supply and how things get worse over time as you recharge it. has any thought or research been given into the fact that the human body creates a lot of heat and using that to,
Sure, a
regenerate?
Stirling engine or something, yeah. No, a lot of people have looked at projects like that, and we look at them all, and somebody's going to crack that nut. I mean, if we can make this thing run on ATP, you just eat a candy bar every morning, Someone will figure it out. You're right, we are a biological reactor. We make so much energy. The heart consumes, your heart generating 100 millimeters of mercury and flowing 5 liters does about 1.5 watts. It's very, very efficient, much more efficient than our device. But yeah, there's energy to be used. We just need smart guys like you to figure out how we're going to do it. Anyway, thank you very much. I've enjoyed presenting. I appreciate your attention.
That was amazing, as usual.
Thanks.
Thank you so much for coming. Taking the time. Well, that was awesome, and there's still a lot more to do. Obviously, when you talk about heart transplant, you have to think of 2 surgical teams. With this, you're talking 1 surgical team, so a lot of things to think about. 8 a.m. You pick the time when you want to do it, so exactly. So logistics of transplant, this will take care of a lot of that. And I think that's what the organ care systems will do too, is allow for better timing, for better surgeries. So again, Billy, awesome job, and it was a privilege for everybody in this room to have you here. And we wish you continued success, and we look forward to hearing the continuation of the story in the next couple of years at our conference. So thank you very much.